Good morning to everyone. In today's video, we are going to see the locus diagrams of series RL, RC and RLC circuits. Okay, so before starting into this series circuits, we just have some little bit introduction about the locus diagrams. Meanwhile, please remember the locus diagram is nothing but the joining of various points, various points of a vector. Maybe it is in current vector or impedance vector, whatever may be. It is a joining of the points by considering one element as variable. In your circuit, maybe the inductor is a variable quantity, or resistance is a variable quantity, or capacitance is the variable quantity. It depends upon the given circuit and given conditions. Okay, so where we use this one, where we require this locus diagrams. This locus diagram is mainly meant for to analyze your circuit behavior, or to analyze the response of your circuit in simple fashion, if I want to say whether the voltage is leading or lagging, the way how we are saying for an inductive circuit or capacitive circuit, those things we are seeing in form of diagram in this locus diagrams. Okay, and these are mainly meant to design the filters or to analyze the characteristics of the transmission lines, all those things. Okay, so now we go for the series circuits. Okay, series RL, RC and RLC. So for time being, please remember the reactance is the only one quantity. Okay, reactance is the only one quantity, because I just want to say here, whatever the impedance, Z is nothing but R plus JX. Okay, R plus JX. If X is an positive value, I can say that it is an inductive reactance. That's why we can give it as an inductive reactance as R plus JXL. If this reactance is an capacitive reactance, I can give it as an R as R minus JXC. Okay, if it is an inductive capacitance, it is plus JX. If it is an capacitive reactance, it is minus JX. Only the variation is the X is varies from positive to negative. Okay, for time being, assume X as reactance. Whether it is an inductive or capacitive, it depends upon your circuit. So to analyze this one, we are having two cases. The case number one is the circuit is having constant reactance. Whether it is an inductive or capacitive, the reactance quantity is constant, but the variable quantity is your resistance. So by varying the resistance value from 0 to infinity, we are going to analyze the circuit. In the second case, we are making the resistance as constant, but the variable quantity is your reactance. I already stated the reactance may be a positive value or negative value. Okay, so here the main condition is whatever the applied voltage, is constant. Okay, applied voltage is constant, and whatever the angle variation, the phasor which is lagging or leading with an power factor of theta. So if anybody doesn't know about the power factor, is nothing but the phase difference between your voltage and current waveforms. Or phasors, we say that it is a power factor. Please remember, we given it is with an angle theta. Okay, so now I am considering case number 2. Okay, case number 2 with constant resistance and reactance is variable. Now I am considering an RL circuit where reactance is nothing but inductive reactance. Okay, so I am considering this circuit. Okay, if you observe this circuit, the circuit is having resistance and reactance. This reactance is the variable quantity. So when I observe this one, if I am assuming this variable quantity reactance, this variable reactance having the range of 0 to infinity, because the minimum value is 0 and the maximum value is infinity. So if I am assuming this reactance, okay, if this reactance is minimum, then the total circuit is having which nature? Resistive nature, the total circuit, because XL is 0. If the XL is 0, there is no need of considering this XL. The only element in your circuit is resistance. Okay, so the total circuit is resistive nature. The current flow in circuit depends upon your resistor element. So V divided by R. Since it is a resistive element, there will not be any phase difference between your voltage and current. So the power factor angle will be the 0. This is case number 1, that where XL is 0, when XL is 0. In similar fashion, if you increase this XL or reactance, if you increase this reactance from 0 to infinity, what about your current? Current is nothing but V by Z. Z is nothing but V by root over R square plus X square. Here I am considering it as an inductive reactance. So when the denominator is increasing, automatically your I value tends to reduce. So now the current flown in your circuit, if I am considering this as an infinity value, okay, denominator as infinity. Now the value will be, the current will becomes anything divided by infinity, it will be 0. So it will be 0, and whatever the current 0 is lagging by an angle of theta. Since it is an inductive value, the voltage value will be lagging, the current is lagging the voltage by 90 degrees. Okay, so now whatever this maximum value of current, okay, whatever the maximum value of your current is nothing but your diameter, Now we just see how this locus diagram will be appears. So observe this circuit. This is your RL circuit, where the XL value, okay, the XL value tends to move from 0 to infinity. So it starts from 0 and tends to ends at infinity. Okay, so when it is in XL equals to 0, the value of your current is nothing but V divided by R, where that current is in phase with your voltage, when it increases, when the reactance value is increasing, the current phasor tends to move. So here I am considering an arbitrary value. Okay, here I am considering an arbitrary value of this current phasor. Where this phasor can be divided on the x-axis as well as y-axis. So the projections of this phasor, on x-axis we given it as an ix, on y-axis we can give it as an iy. Okay, I already stated that the current is lagging by theta. With reference to your voltage. The current is lagging by theta. So when I consider this, the projections can give the sin theta as well as cos theta terms. And if we already know this length is nothing but your IL. This length is nothing but the IL, and this length is nothing but IX, and this length is nothing but your IY. Okay, since it is in parallel length, it is IY. Okay, here we forming a right angle triangle. So I can say that IL square is nothing but IX square plus IY square. So from the right angle triangle I can say this term. What is mean by this IL? IL is nothing but the current flown in your circuit. IL is nothing but the current flown in your circuit. Okay, IL is the current flown in your circuit. So I can state it this one as like this. Okay, I can state it this one as like this. So IL is nothing but V divided by Z, where Z is nothing but the total impedance of the circuit, square root of R square plus X square. Whether it is an inductor or capacitor, it depends upon your circuit. What about your sin theta? Sin theta is nothing but X divided by Z, and cos theta is nothing but R divided by Z, which we can draw from our impedances, because we know that tan theta is nothing but XL divided by R. From this, okay, the projections can give the value of IX, and IY. So IX is nothing but IL sin theta, and IY is nothing but IL cos theta. Okay, so in place of IL I can replace with V by Z. In place of IL I can replace with V by Z. In place of sin theta I can replace with X divided by Z, XL divided by Z. Similar fashion for IL, IY also I can find out. Now from the right angle triangle I said IX square plus IY square is nothing but IL square. Okay, so in place of IL square I can replace with V square by Z square, because I know IL is nothing but V by Z. So V square divided by Z square. So if I want to replace with Z square, either I can go for R square plus XL square. But here the main condition is XL is a variable quantity. I can't go with XL term in my circle equation. So I just want to switch on for the element. So I can know Ix value and Iy value from the locus diagrams. So instead of going with Ix term, because you may ask the question, why you not choose the Z square from Ix, why you choose from Iy only? Because I know the resistance value. Resistance is a fixed quantity. Okay, resistance is the fixed quantity. So Z in place of Z square, I replace with VR divided by Iy. So this is the Z square, I replace with Iy divided by VR. So now I get this term in place of known values, because I know Ix value, Iy value, voltage and resistance. Now if I observe this equation, it is not in the standard circle equation. So to get that, here Iy is term is there, but V by R term is there, one more term. So to arrange this one in a second order term, okay, I just added V by 2R whole square on both sides. If you add this one, the equation by rearranging it will be forms as Ix square plus Iy square minus V by R Iy, which is already available, plus V divided by 2R whole square, which is we added. This equation will forms Iy minus V by 2R whole square equals to V divided by 2R. By observing this equation, we can say that it is similar to our circle equation, which is having the radius V by 2R and center as 0, V by 2R. Okay, so now this is the circle equation. This is the circle equation which is having the center, at v divided by 2r. Okay, on y axis, v divided by 2r on y axis, and radius of your circle is v divided by 2r. This is for RL circuit which is having the coordinates of v on y axis and I on x axis. Okay, in place of inductance, if I replace the circuit with capacitance, okay, the same terminology, the same elements, the same thing will be represented here. The same elements will be represented. Only variation is whatever the angle, okay, whatever the angle theta, instead of the lagging the voltage, it will be the leads the voltage. That only the variation. The rest of the circle, all the terms will be same. The only phase angle, because the capacitance have the leading nature and the inductance have the lagging nature, that theta is only the variation element. This is the locus diagram of the current. Okay, this is the locus diagram of the current locus. Okay, locus diagram of the current. If I want to plot the same thing for impedance locus, I already stated this is a constant resistance and variable reactance. So I just fixing this resistance to a particular value R on RX plane. Here I am considering the plane as RX plane. Previously I am considering it as a VI plane. Okay, based upon your locus, your axis terminologies are varying. Please remember that. In the RX plane, I am just fixing the R value. For particular resistance, I am just increasing the reactance. Okay, I am just increasing the reactance. So here I am just assuming the reactance value as this one. For particular reactance, that is XL1. For this one, the impedance, okay, the impedance will be Z. Okay, Z, you may assume it is Z1 or Z2, whatever maybe. Okay, similar fashion for this particular impedance, XL2, this will be the impedance. Okay, this will be the impedance. This is for the positive values of reactance. This is the positive value of reactances. Already I stated that Z is nothing but R plus JX. Here if X is positive, we call it as an inductive. If X is negative, we call it as a capacitive. For negative X, we call it as a capacitive reactance. So for this, it will be in negative direction of your y-axis, negative direction of your side. So when you observe these lines, if you add all the impedances, it is nothing but a straight line which is parallel to your reactance axis. Okay, which is parallel to your y-axis or reactive axis. Okay, so the same thing we mentioned. The previous case examples, okay, the previous case derivations we done with respect to the current phases. The same derivation we can also do for the impedances. Instead of having the I equals to V by Z, we know that Z is nothing but R plus JX. Whatever the admittance is nothing but the reciprocal of your impedance, which is nothing but G plus JB. Actually, we don't know about what is your conductance and susceptance. Okay, we don't know about whatever the conductance and susceptances, but from the impedance we can able to find out the admittance as well as conductance and susceptances. Here we are drawing for the axis of conductance and susceptance. Previously we find with respect to the current phases we are drawn the phasor locus diagram. Now we are drawing for the conductance and susceptances phasors. So when I observe this, z is nothing but 1 divided by y, I can get 1 divided by g plus jb. So whenever we have the complex term on your denominator, we just go for the rationalization. When we perform this rationalization, okay, this is the final expression I can get. So I just simply separate the real and imaginary terms. From this, I know the constant resistance. I know here the constant resistance. That's why I'm choosing the expression number 1 and rearranging the terms. To get into a standard circle equation, I just added 1 by 2r on 2r whole square on both sides and make it into a standard circle equation. Here the circle equation is having 1 by 2r comma 0 as the center and 1 by 2r as the center for conductance and susceptance locus. So if I draw this impedance locus diagram, this is the circle which is having the center of 1 by 2r comma 0 and with a radius of 1 by 2r. Okay, 1 by 2r on GB plane. Okay, GB plane or conductance or susceptance. When coming to the current locus, if you take the VI plane, it will be like this. For example, if I want to modify this plane in such a way that V is on y-axis, V on x-axis and I on the current on y-axis, the circle equation will be like this. The equation of the circle doesn't varies, only the position of the circle only varies. Please understand that term. Okay, finally the radius is 1 by 2r and the theta is nothing but x divided tan inverse of x divided by r. The active power in your circuit, since it is in AC circuit, impedances VI cos theta is your active power and reactive power will be your VI sin theta. So that's it for your series RL circuit, series RL, RC, RLC circuit for constant resistances and variable reactance.